Hello, so this video is basically going to be an organized overview of astronomy units and useful values. I thought it would be useful to have a synopsis of relevant astronomy constants, particularly around this time of year, as I'm releasing this video near the end of a typical semester or trimester. The terms I will talk about in this video are ones that you'll see over and over again in the field of astronomy.
I feel like an astronaut in what you know about rolling down in the deep.
Units of angular measurement. Let's start with that. Arcsecond. An arcsecond is 1/60th of an arc minute, which is 1 over 3,600 degrees. Radian. A radian is about 57.3 degrees, or 206,265 arcseconds. Angular velocity. So this I really only refer to one term because proper motion is the most common here. Proper motion is often referred to as angular velocity because it represents how fast an object shifts angularly. We usually measure proper motion in terms of arcseconds per year or kilometers per second. Units of length. AU, aka an astronomical unit. An AU is defined as the mean distance between the Earth and the Sun. That's about 150 million kilometers. Parsec. A parsec is the distance at which Earth's orbit subtends 1 arcsecond. In other words, 1 arcsecond equals 1 AU over 1 parsec. This can be rearranged into the familiar equation d, the distance to a star in parsecs, equal to 1 AU over 1 arcsecond. If you'd rather put this in terms of light years, 1 parsec is approximately equal to 3.26 light years. Solar radii. We often use the sun as a reference point for values like radii, luminosity, mass, etc., and denote the solar unit with this point inscribed by a circle. 1 solar radius is equal to 695,700 kilometers. We can use this unit to compare the size of the sun with other stars. For example, the star Rigel is 78.9 solar radii. So to summarize, the most common astronomy units of distance include AU, parsecs, kilometers, and when talking about the size of stars, solar radii. Units of mass. Kilograms. The SI unit for mass is kilograms. Solar mass. As I mentioned previously, we often use the sun as a reference point. 1 solar mass is equal to about 1.99 e to the 30th kilograms. Now, we can also talk about the mass of Earth and the mass of Jupiter. So when talking about the mass of other planets, we sometimes use an Earth mass or Jupiter mass for reference instead of the solar mass. The mass of Earth is equal to about 5.97 e to the 24th kilograms, and the mass of Jupiter is equal to about 1.9 e to the 27th kilograms. Okay, so now let's talk about relevant SI units, besides kilograms, and some of the derived units that we can get from this. The SI unit for temperature is Kelvin. To get from Celsius to Kelvin, just add 273.15. For example, 30 degrees Celsius is equal to 303.15 Kelvin. We can use some of the other base SI units like kilograms, meters, and seconds to derive other relevant units in astronomy. Newton. A newton is a unit of force equal to meters times kilograms per second squared. Pascal. A pascal is a unit of pressure equal to newtons per meters squared. Joule. Joule is the unit of energy or work equal to newtons times meters. Watt. A watt is a unit of power equal to joules per second. For example, the luminosity of the sun is about 3.83 e to the 26th watts. We could also just call this 1 solar luminosity. Constants. So we also have a lot of constants used in astronomy. We'll go over some of the main ones here. Obviously, there's a lot more, but these are just kind of general ones. C is huge. The speed of, not just in terms of the actual value, but in terms of its relevance to astronomy. The speed of light is 2.998 e to the 8th meters per second. G, the gravitational constant G is 6.674 e to the negative 11th meters cubed per kilograms second squared. This is key to talking about the gravitational force between two or more masses. H stands for Planck's constant, which is 6.626 e to the negative 34th joules per second, joules times seconds. You'll likely see this constant when talking about quantum physics and blackbody radiation. Sometimes you will also see the reduced Planck's constant, h bar, which is equal to h over 2 pi. K is the Boltzmann constant, which is usually written either as K or KB. and it is 1.38 joules per Kelvin. It can be found in the ideal gas law, PV equals NKT. The Stefan-Boltzmann constant is 5.67 e to the negative 8th joules per seconds times meters squared. You'll find this in the Stefan-Boltzmann law, as I'm sure you could guess by the name, which describes the amount of power radiated by a black body. The mass of an electron is 9.11 e to the negative 31 kilograms. Well, that covers most of the widely used astronomy units and constants. Of course, there are many more relevant terms depending on which subfield of astronomy you are focused in, but I'll reserve those for a later video. Thanks for watching!
Slow motion, yeah. I feel